So in our last example here, we have y1 and y2 are independent exponential variables with mean 1, and u is their average. And I want to find the density function for u. So there's a lot of words here and not a lot of equations. So the first thing is to try and figure out how do we translate these words into equations. The first thing is to notice that we have exponential variables. Let me remind you of the generic formula for an exponential random variable. An exponential random variable has the following density function. F of y is equal to 1 over beta e to the negative y over beta. And that's as y ranges between 0 and infinity. If that sounds like total gobbledygook to you, if you've never heard that before in your life, that means you didn't watch my earlier lecture on the different distributions. So just go back, and it's the same series, the probability videos here on Educator.com. Just go back and scroll back and you'll see a lecture on the exponential distribution. And so that's what I'm quoting right now. So that was the density function that we learned back in that earlier lecture. And the other thing we learned is that the mean there is, or the expected value, was just beta. That's the expected value of the exponential distribution. And so in this case, we're given that we have exponential variables with mean 1. So that means my density function for y1 is just, it's the function I just listed, except I plug in beta equals 1. So beta equals 1. So I get something fairly nice, e to the negative y1, where y1 goes from 0 to infinity. And the same thing for y2. f2 of y2 is e to the negative y2, where y2 goes from 0 to infinity. And what we are told here is that these variables are independent. What that means is that the joint density function you get just by multiplying the two individual density functions. So using independence, so f of y1, y2, the joint density function, you get by multiplying the two marginal density functions, f of y1 times f of y2, f2 of y2. And so that's e to the negative y1 times e to the negative y2. And let me draw the range that we're looking at there, because that will be something we'll need to look at. They both go, y1 and y2. Oh, look, I got the variable right this time. y1 and y2 both go from 0 to infinity. So the range we're kind of generically looking at is all of this upper quarter plane here. That's my range. And I think I'm about ready to start looking at what u is. So u, in this case, by definition, we're given that u is their average. So what's the average? That means y1 plus y2 over 2. Now I want to find the density function for u, but the whole point of this lecture is to use the method of distribution functions. So the method of distribution functions says you first find the distribution function, capital F, of u. So that's, by definition, the probability that capital U, trying to avoid writing tails on my capital U so that they will look less like little u's, because we have a little u coming right up here. So capital U is less than or equal to some cutoff value of little u. And so now I'm going to plug in what capital U is. So that's the probability of y1 plus y2 being less than or equal to little u. And I said the way you deal with this is you try to convert that into a region, and then you try to find the probability of being in that region. So I want to look at the region where y1 plus y2 is less than or equal to little u, which means I want to graph the line where y1 plus y2 is equal to u. And if I graph that out, I'm going to graph that in red. There's the line in red where y1 plus y2, actually let me not write it right there. There's the line where y1 plus y2 is equal to u, and the intercepts right on both axes there are u. So there's u and there's u. You write y2 a little further down here, and then I can write u right by the intercept there. So we're looking for the region where y1 plus y2 is less than or equal to u. So that's all the region south of this line. So that's all that region colored in red there. I hope you're not colorblind, because it really helps to see the color in understanding these examples. So I'd like to describe that region in terms of values of y1 and y2. I think I'll describe it like this. So first I'll describe y1 is going from 0. The biggest value I see there is u. And y2, I see that I have a small mistake here, in that my u is not y1 plus y2. It's y1 plus y2 over 2. So I need to fix that mistake. So if I solve this, this is the probability of y1 plus y2 is less than or equal to 2u, not u. So let me see if I can change that on my picture. Fortunately, the general shape will be the same, but let me just change all my intercepts there. This is y1 plus y2 is 2u, and each of those intercepts would be 2u. And so my line right here is the line y1 plus y2 less than or equal to 2u. So if you were following along and you got a little confused by that, you were very right to be confused. And now I think it's right. So y2 is going from 0 to 2u. So that should have been a 2u up above. And this should be 2u minus y1. That describes my region now. I think I've got that described right. And so I'm ready to set up a double integral over that region. So this is the double integral y1 goes from 0 to 2u, and y2 goes from 0 to 2u minus y1. And then the function we're integrating, that joint density function that we figured out, is e to the negative y1 times e to the negative y2. And it looks like I've got y2 on the inside, dy2, dy1. Now I've got to solve that integral. It's going to be a little bit messy, but I noticed that my first integral is with respect to y2. The inside integral is with respect to y2. That means e to the negative y1 is a constant. So that's one mercy there. So I'm going to pull that one out of the first integral, of the inside integral, e to the negative y1, because it's just a big constant. Now the integral of e to the negative y2 is negative e to the negative y2. Those are being multiplied. And I have to evaluate that from y2 equals 0 to y2 equals 2u minus y1. And so I get e to the negative y1. Now, if I plug in negative e to the negative y2, well, y2 is 2u minus y1. Negative y2 will be y1 minus 2u. So e to the y1 minus 2u. Minus, now if I plug in y2 equals 0, I'll get 1. But it's minus a negative, so it's plus 1 there. And I think I'm going to distribute my e to the negative y1. Let me keep going over here. So if I distribute e to the negative y1, e to the negative y1 times 1 is e to the negative y1. And e to the negative y1 times e to the y1 minus 2u. Remember, you add the exponents, and so those y1s will cancel. That's pretty nice. So I'll get e to the negative y1 minus e to the negative 2u. Of course, that was all the inside integral, and I still need to integrate that with respect to y1, dy1. dy1. And so the integral of e to the negative y1 is negative e to the negative y1. And the integral of e to the negative 2u. Now, u is a constant because our variables right now are y1 and y2. So e to the negative 2u, the integral of that is just negative y1, negative e to the negative 2u times y1. So that's because e to the negative 2u is a constant. Now I've got to integrate that or evaluate that from y. Where were my limits on y1? Oh, they're over here. y1 equals 0 to y1 equals 2u. So let me plug those limits in. So the first one, I get negative e to the negative 2u minus, now y1 equals 2u, so minus 2u e to the negative 2u. Now y1 equals 0. I have minus a minus, so plus y1 equals 0 gives me just e to the 0, which is 1. And my last term is just 0 because of the y1 term. And I think I've finally figured out my distribution function. My capital F of u is, let me rearrange the terms a little bit, get the positive 1 at the front. 1 minus e to the negative 2u minus 2u e to the negative 2u. So that's my distribution function. The goal here was to find the density function, but fortunately I've done the hard work. The density function you just get by finding the derivative of the distribution function. So f prime of u, and the derivative of 1 is 0. The derivative of e to the negative 2u is negative 2 e to the negative 2u, but I've got one negative, so it's positive 2 e to the 2u, or e to the negative 2u. Now I've got to use the product rule. So minus 2 times u times the derivative of e to the negative 2u, so minus 2 u e to the negative 2u, plus e to the negative 2u times the derivative of u, so plus e to the negative 2u. And surely some of this simplifies. I see that I've got 4u e to the negative 2u, and I've got 2e to the negative 2u minus 2e to the negative 2u. So those cancel, and that's my whole density function, is just 4u e to the negative 2u. And let me put a range on u. Well, y1 and y2 are both going from 0 to infinity, which means their average will also go from 0 to infinity. So I have found a density function, just 4u e to the negative 2u. And let me box that up and present that as my solution. All right. Let me go back and go over the steps there, because lots and lots of steps of this problem. So we started out with independent exponential variables. What's an exponential variable? Well, fortunately, there's a whole lecture on exponential variables earlier on in this series here on the probability lectures on Educator.com. Go back and check it out, the earlier lecture on exponential variables, and you'll see the definition of the density function was f of y is 1 over beta e to the negative y over beta, and the mean there is beta. So in this case we have mean 1. So that's why I plugged in beta equals 1, and I just got, for my density function for y1 is e to the negative y1, and similarly my density function for y2 is e to the negative y2. Now, independence means that the joint density function you get just by multiplying the marginal density functions. So I just multiplied those together, and now I wanted to find the density function for this u, and it says that u is their average. So the average of y1 and y2 is y1 plus y2 over 2. To find the density function, I'm going to first find the distribution function. So that means the capital F is the probability that capital U is less than some cutoff value. And so then I plugged in the definition of capital U as y1 plus y2 over 2. And now I simplified that into, I just moved the 2 over, so y1 plus y2 is less than 2u. And I wanted to figure out what region that's describing. So I graphed the line y1 plus y2 equals 2u, and there it is in red right there, that red line. And I found the region less than that, and I tried to describe it in terms of y1 and y2. So first y1 goes from 0 to 2u, and then y2 goes from 0 up to that diagonal line. So if you write that in terms of y2, you solve that and you get y2 is equal to 2u minus y1. So that's where those limits came from. And then those limits turn into the limits that I use for the double integral. So those got used right there. And then I used my joint density function. That's what I'm integrating. And now it turns into a somewhat messy Calculus 3 problem. If you don't like doing all the Calculus 3 and you want to throw this into an integration program, that's totally fine with me. If you want to throw it into an integration program, you should end up getting the same thing I do for the distribution function. I integrated with respect to y2 first. Of course, e to the negative y1 is a constant at this point. Plugged in my values for y2. That's a little hard to read. Let me see if I can write that a little more clearly, because that was a u. So there's a u. Oh, that's much better. And plugged in the values for y2 and simplified it down a bit. I distributed this e to the negative y1, which is how I got this function right here. Still have to do the integral with respect to y1, so I did that integral. Remember that u is a constant, so the integral of e to the negative 2u is just e to the negative 2u times y1. And then I plugged in my values for y1 and simplified it down, and I got my distribution function. That's still not the density function. You get the density function by taking the derivative of the distribution function. So I took that derivative, had to use a little product rule here, which made it get a little messy. But then it turned out that some terms canceled, and I got a fairly simple density function, 4u times e to the negative 2u. And of course, my range on u, it's all the possible values of u, which since u is y1 plus y2, y1 plus y2 over 2, that could be as small as 0 and unboundedly large, so we have to say the range of u is from 0 to infinity. So that wraps up this lecture on distribution functions. Remember that distribution functions is the first of 3 methods that we're going to use to find the distribution and densities of functions of random variables. So distribution functions is the first one. That's what we've just been talking about. The next one is the method of transformations. So I hope you'll stick around for the next video. That will cover the method of transformations. And then the third method is moment generating functions. So I've got another video coming up after that about moment generating functions. They're all sort of different techniques to solve the same problem, but they sort of work, some of them work better in different circumstances, which is why we learn all 3. So this is part of the larger chapter on finding distributions of functions of random variables, and that in turn is part of the whole probability lecture series here on Educator.com. I've been working with you today. My name is Will Murray, and I hope you'll stick around. Thanks very much. Bye-bye.